Welcome to Breadboarding. This is the ninth in a series of videos to create a simple 8-bit microcomputer on solderless breadboards and learn how computer hardware works. In this video, we're going to be taking all of the components that we've created previously, so the main board with the CPU, the RAM, ROM and peripheral interface adapter, and we're going to hook up the 7-segment display and decoder logic and also plug in the keypad. Then we're going to power it on and see if it all works. So here's the NanoComp. You can see this is pretty much as we had it before. I've still got a logic analyzer hooked up to both the data bus and the address bus, and we'll have a look at that in a little while. But first, what we need to do is to plug in the components we created in the two previous videos. So one of those is the LED display, and this also includes the Darlington driver and the decoder that is used to select whether we're scanning the keyboard or which of the digits we want to display. What I have done is replaced the right angle connectors here, and that to hook this into the main board here was actually easier using this ribbon cable than it was using the right angle connectors. We'll leave the right angle connectors for the keypad, and on the keypad I have plugged in a number of cables, and I've also then plug these cables into the right angle connectors, which we're then just going to plug into the address decoder there. We're going to plug this in first of all, and we're just going to do that quickly. It shouldn't hopefully take too long. So as I've said in previous videos, what I've tried to do is to retain some of the color coding that the logic analyzers use, in that they tend to start with the channel 0 is purple, then channel 1 is blue, channel 2 is green, yellow, etc. So it just makes things a little bit easier when hooking things up so you don't make mistakes. So what we're going to do here is the PB, you can see here the B0123, so 0 is the purple. We need to plug those into the PB port over on the PIA here. So we're just going to plug those in, making sure we get them the right way. 0, 1, 2, and 3. Let's just make sure we're okay there. Yep, PB0. Now we expect to have a gap with PA7 here because that is not used in this particular design. So now we're going to hook up to PA0 these cables. So PA0, PA1, green will go to PA2, then we go yellow, then we go orange, then we go red, then we go brown. Just make sure there that yes, so we have a gap there for PA7, PA6 is connected. And then these other two wires are the reset and the non-maskable interrupt. Now, at the moment we don't have any signal for those to plug into, but what I have done is got some wires here already, and all we're going to do is to plug in a lead going from non-maskable interrupt, which is this line here. So we're just going to that in there. That's non-maskable interrupt, and the non-maskable interrupt is the black line, not to be confused with ground. And then reset is this line here. We're not going to distinguish between reset button and reset at the moment, but what I will be doing is perhaps adding a separate circuit for debouncing the reset switches at a later point in time. So we're just going to do reset pin next to that. That is reset done. Okay, then we need to hook up the power for this board. So we've just got the red and the black for those. And what I have got, as I've said in previous videos, this is my little voltmeter that I talked about in the tips video. And we're just going to plug that in. What I tend to do is to plug this into new bits of board that I'm fitting in, just in case the voltage drop on it is too much. And as we look to expand this design, we'll have to sort out the power distribution. properly. But for the moment, we're just going to work everything off the main CPU board here. And now we've got the keypad. So we need to plug in the Q line. So this is Q 0 to 1. And those are just going to go in at the top here. Make sure that's all okay. Yep. And then the other lines here, which is the A0 to A5, non-maskable interrupt, ground, and reset. We just need to make sure we plug these into the right lines. Right. What I also just need to do is to check that all of the jumper cables here are all seated properly. I'll explain why in a minute, but all those appear to be seated properly. We appear to have everything in. So what I'm going to do now is to plug in my USB power cable. So I'm just going to plug this down the bottom here. Make sure we plug red to red, black to black. And now we're going to plug in the power. And if this is working, what we'd expect to happen is to see a minus sign on the display up here. So I'm just going to plug in the power, see if things are working. Great, so that does appear to be working. That's a relief. Now, the only issue here is that it's a bit difficult to see the LED display here. So all I do have is a filter which might make it a little bit clearer. I might need to change down the brightness of the camera so it doesn't show the rest of the board quite as clearly, but it probably makes the display a little bit easier. And you can also see here that my little voltage meter is reading about 4.95 volts, so that shouldn't cause any problems. So I'm not going to do a massive amount of testing here, but I am just going to do a few things. So the keypad here, we have a reset button and abort button, and the go button is what I'm going to be using for doing some basic tests. So what I want to do is when I type go, I should get a G, and then I'm just going to type in a number of digits. Going to start with A, B, C, D. Now, we won't see the fourth one because then it will try and execute the code at that particular point. So what I'm just going to do is then do D, 7, 8, 9. Oops. 7, 8, 9. And if you can see, some of the characters are not quite right. Now, what the issue here is that we know when we were building the 7-segment display that the E and F segments here and here are transposed. So we are expecting that to be an issue. So let me just go back to D. See if it should show D, 7, 8. And then we'll go to 9, E, 4. You can also see that 4 is also showing the problem. And if we then show 5, 6, 1, so you can see also that 5 is showing this particular issue. And then if we do 2, 3, and 0, you can also see that 2 has the problem as well. So this was the problem that we were expecting. And what I'm going to do now is just go back to the screen share and show you a little bit about this. One of the other issues that I tried this out first before I went to record it, and there was one issue which was quite confusing, which I'll just show you now. What I'm going to do is just turn this off, and I'm going to make one small change, and then we'll look at how we were able to diagnose what the problem was. Basically, what I've done is disconnected one of the wires, which was loose when I first tried this out, and this is one of the problems with these jumper cables, is that they sometimes do come loose. When I first powered this on, I didn't see anything occur. And so what we did in this particular situation was to run up the logic analyzers. You can see we've got logic analyzer on the address lines, and I've also got a logic analyzer on the data lines. It's also telling me there's an update available, which I won't do at the moment. We can also see the data lines. So what I'm going to do now is just press the reset button. And then what I'm going to look at here is the values that we're seeing here. And what we can see on the data is 7D89 8486, and if we look on the address lines, we can see that we have 7FFE, 7FFF. Now, our reset vector was 7D89, but then it seems to be going to 7C88, 7C89, and that was quite confusing. Obviously, something's not quite right here. Well, it was a fairly simple issue to fix, and what I'll show you now in the slides here is what the issue was and how we went about finding what the problem was. The reset vector was 7D89 on as expected, and what we would expect is the memory locations here would have 10CE 13D0, and what that is load the stack pointer with 13D0. What we actually saw was 7C88 with the values of 84 and 86. Now, I have a copy of the decompiled code, and I was able to look at that, and what that 84 was in actual fact was the second byte of store A to X. Take the contents of A and put it at the location pointed to by X. Now, that doesn't make sense to be the first instruction to be executed, but obviously wouldn't result in anything working properly. So what I then did, it was looked at the 7D89 that the ROM was certainly providing as the reset vector versus the processor was trying to run the code from 7C88. And if we converted these two numbers into binary, and I just used the Windows calculator in programmer mode, if you put in hexadecimal, you can just type in 7D89 and it will show you what the binary values are. And I just put these one on top of the other. And what you can see here is the difference between these two numbers is that the least significant bit there is always 0. And what that led to me to realize was that obviously the ROM is providing the correct reset vector, but when the processor picks that up and then uses it, it's missing something out there. And this is typical of the type of problem that you might have when you're trying to diagnose these sorts of issues. It does take a little bit of deduction to work out what's going on. So what was fairly obvious there was in fact that the processor wasn't seeing the least significant bit, and pin D0 seems to be disconnected, which if you remember what I was just showing beforehand, I disconnected this pin. So if we look at the top-down view, we can see this is the pin. I'm just going to turn off everything. We're going to plug this back in. Just going to plug pin 0 back in, D0 back in. So this is typical of the troubleshooting approach that you need to take sometimes for these. And problem tends to be is if you try and fix too many things at the same time, you tend to get a bit lost, which is why I tend to build things up a piece at a time. I knew this was all working before we started to do the 7-segment display and the keypad, so it must have been in moving things off the board here, probably something got disconnected. Right, so now we're just going to plug this in again, and what I'm going to do first of all is to get the logic analyzers lined up again, so we can then see what the values as we would expect to be. Now I'm going to plug in the power, and the logic analyzers should then, we go. And if you can see here, we've now got the prompt. And for example, if I type in memory here and then do 7FFE, you'll see that this says 7Y in fact in there, but it would be 7B if the segments were released. And then if we go to the next one, then that should be 8-9. So the only issue we have now is reversing our segment E and F that we need to do. And if I just switch back to we can see that we get 7FFF and 7FFE. Then we get 7D89, 8A, 8B, 8C, 8D, 8E. So it looks like the address is progressing as we expect. Then we get some memory accessing in the 1300 address range. And eventually down here, we'll start to get, hopefully, we'll start to read the memory for the display. So I think 13FE is one of the display segments. So that's working there. And if we switch over to the other logic analyzer, we can then see we get 7D8, 9, 10, CE, 13, D0. So after the reset period, you get 7D8, 9, 10, CE, 13, D0. If we go back to my slide here, we can see that in fact the 10 CE 13D0 is what we would expect. So it was just down to a loose wire, and it's typical sort of things. Some of the comments that people have made about using breadboards, this is one of the common sort of problems. What I would say is using jumper cables, this is one of the disadvantages of jumper cables. But when we come to hook everything up using buffer chips and things, then we'll put custom fitted cables and wires, and these will be much more reliable. We're just going to go on to the next page now and look at the E&F segments. So the Nanocomp design expects E&F reversed compared to the 7-segment LED datasheet. As we've seen, the character values affected were 2, 4, 5, 9, and D. If we look at the pin out of the 7-segment display, we can see that E is pin 1 and F is pin 10. And what we're going to need to do is look at the fritzing layout and see what we need to do to make that change. So I'm just going to go to fritzing here. So if you remember, what we want to look at is pin 1. So if you hover over there, that is E, 7-segment, pin 1. We click on that, then that is going over to here, which is pin 16. And if we go to pin 10, which I believe is this one here, that's F. Click on that, and that is pin 17. So in fact, all we need to do is to switch this wire to there and this wire to here, and we'll change around these labels, and the issue should be addressed. So I'm just going to make this change now. So we'll make that change from there to there. And we're going to make this change from here to here. I'm also just going to change the label here so it's accurate. We're just going to change F to E, V to F. So we're just going to fix the issue with E&F. So we just need to turn the power off. Remember that we just need to swap in 16 and 17 around. This is easier said than done here. So there's F and E here, and this is the only trouble is stacking things up like this. What should be quite a straightforward thing is not quite a straightforward. So I think the easiest thing to do here is we're just going to unplug these so we can see where we are. There we go. So this is the one that is going to pin 1. This needs to mount that one and go in further down. We need to reconnect these other ones. Yeah. This one was A, and then what we actually need to do here is make this one slightly longer. What we need, we've got a little bit of room there to make that longer. Like that. I have sufficient there to do the job. Yep, that should do the job there, and then we're just going to plug this back into A. One C, and this one I think G. Let's just, it's probably the easiest way to do is just to see it, turn it on and see if it works. So we put our, we do a G. So the ones we want to try was 2, 4, 5, and 9, D. There we go. So that seems to be resolved. Now I'm just going to go through, do all of them again. So A, B, C, D, E, F, 7, 8, 9, 4, 5, 6, 1, 2, 3, 0. Yeah, that's done. As you can see, we have now corrected the issues of the characters 2, 4, 5, 9, and D, and we did that just by swapping around, and we've also changed the fritzing diagram so that now actually reflects the correct pin assignment. What we do need to do is to change our schematic, so we need to swap in our schematic, we need to swap 7 segment pin 16 and 17 on Darlington IC. There we go. Okay, so that is that. So we've assembled NanoComp. It's now working, and in the next video what I'll be doing is showing some of the commands and some of the built-in programs. There's some simple programs and games, not particularly exciting games, but remember this comes from 1981, so the typical home computer in that time was a ZX81 and the ZX80. The ZX81 had only just come out around July 1981, so this is the type of computer that people were using. Nothing as fancy as a Spectrum or a Commodore 64 for any of those sorts of machines. So in the next video, we will be going through the monitor, looking at the various commands and some of the built-in programs, and I'll also then start to look at the disassembling the binary dump of the monitor so that we can then look at the source code, the assembly language source code of the monitor, and then so we can start to look at perhaps making some changes and improvements. In particular, one of the things I'm going to do first is add a serial port to the NanoComp so that we can upload and download programs which we compile using a cross-assembler on a PC. In that way, we can develop programs a lot more easily than we can using just a keypad and the 7-segment display. But what I will show you in the early stages of this is it is possible to do machine code programming and write software without needing another computer. It's just a little bit laborious, and I think when we go through that, you'll see how big an improvement using an assembler is over doing hand assembly machine code. Thanks for watching. Please hit subscribe so you didn't miss out on future videos, and please also hit like as well if this is of interest to you. It helps to promote the channel and get more people able to see it. Thanks for watching.